This video is about the volume of prisms. You can find it in your text in parts of section 12-1 and 12-3. Recall when we introduced the idea of area that we defined area as the number of squares it takes to cover up a two-dimensional shape. And we started by actually just counting squares. And when we counted up all the squares, that was the area of the shape. And eventually we were able to develop some formulas for the area of different special shapes. So if area is the number of squares that it takes to cover up a two-dimensional shape, now volume is the number of cubes it takes to fill up a three-dimensional shape. Think of these as little sugar cubes, and we're going to fill up a three-dimensional container with sugar cubes. That's what volume means in cubic units. So we can start out to find the volume of something by simply counting the number of cubes in that shape. For example, this is a rectangular solid, so it's kind of hard to count the cubes that are on the inside of this, but if we cut it up into slices like this, we can count the number of cubes in one slice. This is a 5 by 4 rectangle, so that's 20 cubes in one slice, and then we have 4 slices like that, so 4 times 20 would give us 80 cubes in all, and so the volume of this figure would be 80 cubic units. So will it be possible for us eventually to move from counting cubes into developing formulas that we can use to find the volume of common or special figures? Yes, it will. But first of all, we're going to go through some new vocabulary. A prism is a solid three-dimensional figure with two congruent parallel bases. So what are the bases? Well, the bases are the two faces of the prism that are congruent and parallel. So our definition is a little bit recursive there. But as you can see, each one of these solids has at least two faces that are both congruent and parallel. This has two triangles, therefore it's a triangular prism. This prism has two rectangles that are congruent and parallel. It's a rectangular prism. And this has two circles that are congruent and parallel, and it's a circular prism, otherwise known as a cylinder. Really, there's no difference between a cylinder and a circular prism. Okay, some more definitions. We have lateral faces. The lateral faces are the faces of the prism that are not bases. So basically all the rest of the faces, they're not the two bases. The lateral edges are the edges of a prism that are not base edges. So for example, on this triangular prism, the base edges would be the edges of this triangle and this triangle. The lateral edges would be, you can think of it as the line segments connecting the top base with the bottom base. An altitude of a prism is the perpendicular distance between the prism's two bases. So if I measured the distance from the plane containing this polygon to the plane containing this polygon, I would measure this perpendicular distance, and in the case of a right prism, the perpendicular distance or altitude is the same as one of the lateral edges. It's simply the measure of a lateral edge. The other kind of prism is an oblique prism. That's a prism that's kind of squished over to the side like this. And it's not true in an oblique prism that the lateral edges are also altitudes. The altitude would be a different measurement. It has to be the perpendicular distance from the top base to the bottom base. And in this case, the lateral edges are not perpendicular to the bases. So which one of these figures are prisms? Well, a sphere is not a prism. A sphere doesn't have any faces at all. A cube is a prism because it has two parallel bases that are congruent to each other. A rectangular solid is also a prism. Two rectangles parallel to each other. Now, what about this one? We saw a cylinder in an earlier slide, and this one has two bases, but this solid is tipped on its side, so it might be difficult at first to recognize these two as bases, but really they are. Because they are two faces that are both congruent and parallel to one another, they qualify as bases. So yes, this is also a prism. Here's an interesting one. There's a hexagon, it looks like, that is congruent and parallel to another hexagon, and that is a prism. What about this one? We do have a base here, but there's not another base. There's no other face of this solid figure that is even a face, let alone parallel to this face. So this cone is not a prism. Neither is this pyramid because there is no face that is parallel to the base here. Same with this triangular pyramid, not a prism. But this triangular solid has two triangles that are both parallel and congruent, and those are connected by these lateral edges. This qualifies as a prism, a triangular prism. Okay, so back to volume. We've said that the volume of a figure is the number of cubes it takes to fill up a three-dimensional shape. So can we develop some formulas now for volume? Before, when I had us slice up this combination of little cubes into four sort of layers here, I was giving you a hint as to how we're going to develop a formula for volume. Because what we did when we counted the layers, 1, 2, 3, 4 layers, was we were actually measuring the height of this solid figure. So if the height was 4 layers, then what did we do back when we first counted these cubes? Well, we multiplied 4 by essentially how many cubes are in one layer, which is the area of one of the bases. So using this idea, it looks like we could develop a formula that would give us the volume of different three-dimensional solids. Let's look at this figure here. Is this a prism? Well, even though it has kind of a funny shaped base, it does have this base, and it does have another base at the back here, parallel to it, and both of those bases are congruent to one another, even though we don't have a name for this kind of shape. And intuitively, you could think of cutting this figure up into slices this way. How many slices would there be? Well, it looks like we have 1, 2, 3, 4 units in this direction, so there would be 4 slices. And each slice would have an area of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 square units. So 11 square units per slice here, and then we have 4 slices deep. So the volume is actually going to be the area of one of the bases, which we've calculated here, times the height, which is just how many slices, in this case 4. So in this case, the height is running in a back and forth direction because the height is simply defined as the number of slices or the length of the lateral edges. What about prisms like these, where we can't simply count the squares on the bases? to find the area of the base? Well, just like we did with the area of two-dimensional figures, we do have formulas for the areas of some two-dimensional figures that don't have countable squares. For example, a circle. We have that the area of a circle is pi r squared. So since we know the area of a base, we can find the volume of this by multiplying the area of the base times the height, which in this case is 4. In this figure over here, it might be very difficult to calculate the area of this base, but if we could somehow find the area of that base, we could still multiply it by the height and get the volume of this funny shaped solid figure. Here as well, we have the area, a base with some area that we could calculate somehow, and this diagram has this marked as the length, but we know that we are going to call this the height because what it is the measure of the lateral edges. It's the distance between the two bases. So we can generalize this. The volume of any right prism, including ones with funny shaped bases like this, as long as there's a right angle between the sides and the base, the volume of any right prism is going to be the area of the base times the height being the distance between the two bases. And that will be in cubic units. Why cubic? Well, the number of cubes. We're counting cubes, so we're counting cubic units. Let's do an example problem. We're asked to fill in the missing value in this table, which refers to the dimensions of a rectangular solid. So let's just quickly sketch a rectangular solid so that we can visualize what's happening here. We have a length of 5x, a width of 4x, and a height of 3x. Now, does it matter which I'm labeling length, width, and height? In this case, it doesn't end up mattering because any way that I rearrange these three numbers, I'll end up with the same answer for volume. But in this case, since the problem is telling us which measurement we're to treat as the height, we'll just go with that. And we'll write our formula using the measure of the top and the bottom faces as the bases, and then this measure as the height here. So the area of the base then would be 4x times 5x, because we have length times width for a rectangle, and then the height would be 3x. So the area of the base then is 20x squared. Don't forget that we have two x's multiplied together here. The height is 3x, so the volume then is 3x times 20x squared, which gives us 60x cubed, and it's no coincidence that we call this cubed because we are working with cubic units for volume. You try this one. Fill in the missing value in the table, which also refers to a rectangular solid. For further practice, see page 478 of your book, numbers 23 and 27, and page 492, number 5.